Hi, good morning. Am I audible?
Hi, Farhan. Yeah.
Okay, cool. Um, so the link for today's notebook is in the chat box. Okay, so please open this notebook and then we will wait for a few minutes before we start. Yeah, I'm waiting for everyone to join, and you can find the link to today's notebook in the chat box. Please open it in Google Colab. Okay, so I'll start.
Just Farhan, one question. So it is W4S1 football underscore V3 or V2?
It's V2.
Okay.
It's V2. V3 is more about what we'll do tomorrow. Yeah. So please get the link from the chat box and open the notebook. There are two versions, foosball minus V2 and foosball minus V3. So we are going to work with V2 today. Okay, so what is the general agenda for today? So till last week we were working on algorithms. So we saw SARSA, we saw Q learning, and we tweaked the parameters a little bit. With trial and error, we were able to find solutions to the, you know, to we were able to find solution to the problem of scoring a goal in the football arena, and it took us, I think, about 2,000 steps or so with the right parameters to converge, right? Um, so we have a few techniques that we can use, and what we want to do now is we want to make the environment more realistic. So in the beginning we said we are getting started with foosball because it's a very tiny static environment, and we just want to see how we can come up with algorithms that can operate in this environment, that can control an agent and let it learn planning and control. That seems to be working now. So the agent is able to find the shortest path, It takes around 2000 steps, which is sort of okay because reinforcement learning algorithms are generally slow in the sense they take a lot of iterations, lot of babysitting, lot of parameter to get them working. But because this is a small problem, so we are able to run it, train it in under a minute, and then it does an okay job, right? uh, so the focus for today is going to be how can we make the environment more realistic. And one of the things that we can do is add uncertainty. So far what we have been doing is that whenever you take an action, we are certain about the outcome. We know what the next state is going to be with 100% certainty. So the first bit that we want to change is introduce some probability there. So whenever you take an action, it's very likely, you know what is the most likely outcome of that action, but then there are some less likely outcomes as well that are possible. So if you look at the description, and I have highlighted things that are going to change. So over here it says that movements have some uncertainty associated with them. What that means is that whenever I take any of these four actions, so there is a small chance that the intended result, I won't get the intended result. I won't reach the intended state. So, and if you scroll a little bit further in the rules section, so there is a little bit more detail. So what is going to happen now is that when you select a direction for movement, so you aim for a particular state, particular next state, and you take an action accordingly. Earlier, the ball used to go to that state with 100% certainty, right? Given that the state was a valid state. Now that is not going to happen. Now we will introduce a little bit of error or a little bit of uncertainty or probability. And what will happen is that, say, with 80% or 90% probability, the action will indeed result in the right or desired state. But with a small probability of, say, 10% or so, you will end up in a different adjacent state. And we will still keep things simple. We won't make a lot of changes at the same time. So the way we want to do this is we want to introduce another hyperparameter, which is which we are calling slip probability. So it's like the ball slipping. Instead of going to the right cell, it will slip and it will go into an adjacent cell, adjacent position, right? So slip probability is basically that small probability with which the ball will go into one of the wrong states. So, and one minus slip probability is the probability with which it will go to the right or desired state. Okay. And what we want to do is basically modify the class. We already have a lot of code written, so we want to write don't want to write everything from the scratch again. But these are the changes that we want to make. So the first change is that now the constructor for the class is going to take another parameter which we will calling slip probability. uh, and the idea is that if this probability is set to 0, then the world becomes deterministic as it used to be so far. But if it is non-zero and if it assumes any value between 0 and 1, then there is going to be a little bit probability that the actions don't have the exactly the intended consequences. So the first, there is one modification over here for the init function. Then we are introducing a new function that we are calling set state transitions. This will just take this parameter slip probability and it will create a 3D table or a numpy array. Why is this needed? So earlier, whenever I wanted to find the state corresponding to a transition, I would look at the current state and the action, and that would give me the target state. Now, every time you pick a state and an action, there is going to be a distribution of target states. So for example, if I am in the starting cell and if I try to go east, then uh, technically there are 20 different possibilities, although we will restrict that somewhat. So um, but technically the ball can end in any of the other states. What we want to do right now is that uh, we will write the code in a way so that, say, with 90% certainty, if you take action east, the ball is going to get into state 1, and with 10% probability it will try to go up or try to go west or try to go down, and depending on the case, it will end in a different state, right? So basically now this is going to be a 3D table uh, that we want to pre-compute, and this is pretty much like the p table or the single step dynamics that you would have seen when interacting with the taxi environment. So the idea is same. uh, this is the second change, and yep, so that the p table will be populated within this function. And yep, the other change is that the function that we had implemented, the method that we implemented earlier, which we used to call get next state on action, we are going to rename it to get likely next state on action. So the body of the method is going to be exactly same, because it will just it will tell us what the next state would be if the action was executed, like if the outcome was deterministic, right? So if there was no other possibility, no slipping, so what would whatever the outcome would be. So the code inside the method is going to be the same, but we will just rename it to get likely next state. And then we are going to redefine get next state on action, and this redefinition will require us to sample the next state. So imagine that for any state, any action, there are 20 different possibilities for the next state, and with each possibility there is an associated probability that we have pre-computed in the p table. So using those probabilities and using an numpy api, you can pick one of those states. uh, this is the last bit of change that we want to make over here. Um, Yep. So we'll get down to implementing these changes, and once we are done with the environment, we'll again like verify that the environment is behaving like we expect it to. And after that, we'll go over the same algorithms that we implemented earlier, and we will see if there are any changes that are required. And those changes could be in terms of the logic or in terms of the parameters or hyperparameters. We'll see if we can converge in this case as well, right? So, and this is going to require a little bit of thinking and trial and error. But I hope the instructions are clear. Let me know if there is any confusion. We will break out into rooms and we'll take a good 15-20 minutes to try to implement this.
So Farhan, one question. When we are building the table with the returns, given that for each state action pair, there's a likelihood of landing in a subsequent state, right? So when we compute the discounted returns for future states, do we just pick the state with the highest probability, or we do some sort of weighted average of the probabilities versus the future rewards for different states?
Yeah. So it turns out that both approaches are valid. We can stick to the earlier approach with that where we were just picking the maximum, the most likely action. We can also do a weighted or expected value instead of taking the action, instead of taking the return value corresponding to the best action. We can take an expectation. So we multiply the different actions corresponding to their probabilities. But that is not going to be impacted by the introduction of this table, because once you have decided what the action is, you simulate the action, and then you already know what the next state is, right? So once you take the action, there is no distribution, right? Because it will be just a single state.
But in SARS, we take the action, right? But with Q, with the
Q
other
learning.
one, yeah, we don't really take that action, right? We just
Right.
okay.
Right. There is a third algorithm that we will try to implement today, which sort of does something similar. It doesn't really take these probabilities into account because we don't really have access to these probabilities, right? This is part of the environment. Uh, we don't want to learn them. We won't be able to learn them. But what we can do is we know that there are different actions possible in the next state. So one possibility is to take the best action. Another possibility is to take weigh those actions by their probability. But the probability that we are going to use will come from the policy that we are using, which is if you're using an epsilon greedy policy, then we will pick the probabilities corresponding to that policy basically.
Okay.
Okay. All right. So I'll start the breakout rooms. Let us try to implement this. Okay, so unfortunately there was some issue with the audio in the breakout rooms. I wasn't able to hear you. Sorry about that. But I hope everyone was able to get at least some time to at least think about a solution, right? So the idea is really simple. It's a 3D table. We sort of understand how to populate it. So I'll go step by step and try to explain my solution, right? So if you look at the to-dos, it says that first of all we have to modify init to take this additional parameter, right? So go to init and add another parameter, and the default value is 0. Okay. Then init is already calling this method that we have to implement. That is already done. Okay. What we really have to do is to implement this method first, and then there are a couple of other changes, right? So because we need to populate this table, which is a three-dimensional table, so obviously we need to write at least 3 loops, which are, I'm just copy pasting, but which are going to look a bit like this, right? So the top loop goes over the state, the current state, and then there's actually an if condition, which you have to put here because you don't want to do anything with the terminal states. You don't want to update or set transition probabilities for terminal states. So excluding those states, the second loop is for the actions, right? So this goes over all the states and all the actions, right? Um, what the rest of the code? Let me first copy the rest of the code and then try to explain it. Right. So I just added quite a few lines from 118 to 126. But there is an additional loop over here because we need to make a distinction between the actual action, uh, uh, you know, for that was executed and the action which actually happened, right? So this is the loop for the actual action, and then within that loop there is another loop that is checking for whether this was the intended action or not, right? And there are two cases. If this was the intended action, then to get the next state we are calling this method, which we simply had renamed earlier, right? So if this is the intended action, then just get us the state, next state, and then corresponding to that next state we are updating this table self.p with a probability of 1 minus probability slip. This is what we discussed earlier, right? So this, assuming that probability underscore slip is a small number, 1 minus probability slip will be a comparatively bigger number, larger number, right? This is what is happening here. On the other hand, the uh, if we are populating one of the other actions which was not the intended action, then this will look a little different. So again, we execute that action. We're calling it bad action. So we execute that action, and then we get the next state, right? And what really happens here is on the left hand side, you have to be careful about this because uh, the way we are populating the table is the action that goes here is the actual action, the action you performed, right? You tried performing, but the probability over here, it comes from the next state, which that actually happened because because the outcome was different. So this is roughly how it looks like.
So in this case, why are we trying to normalize probability of slip by self dot next actions? So do we need to normalize that?
Yeah. So because there are 20 states, so if I say that probability slip is zero point 0.1, what I essentially mean is that zero point 0.1 gets distributed over the 19 bad states, and zero point 0.9 goes to the only correct state.
So the problem with this though, so I wrote this first and then I kind of actually went and changed it because based on how you described the problem on the edge conditions here, when you go off the map, they're actually going to vote back into the main state. So you're going to end up with more than one minus prob slip. So what I did is I actually I created a list of possible states, right?
Mm-hmm.
So if because it's not, you shouldn't be divided by num actions. It should be divided by possible states, right? Because if you go through and say, well, I could possibly land in these three states. One of them is the right state. And that should get your 0.9. And then all the other ones you should divide. But which is right? Because based on the comments in your notepad, I kind of figured the second, like what I ended up doing was right, but I had also implemented this like you, which is more right from, what people would do in RL generally.
Yeah. So one thing that we need to consider is that in this scenario, although we have the way we have created the table, we can assume that you are likely to get into any of the other states, but a more realistic setting will be where you can only slip into one of the adjacent states.
Right, but I'm still saying that's the point, right? Like, so let's say you're in the top left corner. If you're in the top left corner, what you've done is you've made it it's a random action. There's a 0.1 chance of a random action. Whereas if you think of it like a random chance of hitting one of the bad states, right? Because really if you're in the top left corner, there's three potential states, right? So the question is, you have these three potential states, your action points at one of them, right? Correct. So let's say I went south. My action points to south. I think a better example is, let's say my action is north. Like I wanted to go north. So let's say I wanted to go north. That's actually off the border. So north and east both yield the same value, right? So the problem is that if the way you've written it here, the probability of going to north is actually like the probability north and east are kind of hitting the same bucket. So you end up adding prob slip over n actions -1 twice into coming back to state 0. So because both north and east yields that. It's the difference between having a random action and a random destination.
Outcome, right.
So which is more, like, I guess my question is, when I read your comments, I determined that from my understanding of your comments, it was that you wanted a random outcome, not a random action.
Yes. Action is actually going to be fixed because action gets performed by the agent, right? So if the agent kicks the ball straight, then the action is basically east. The outcome has to be probabilistic.
So then in that case, it's more like, so what I did is I just actually created a list of possible states and then distributed the probabilities accordingly. So it's, it's very similar to this, except it was like, instead of if action is bad action, it's if, desired state, if like bad state is equal to desired state, then,
Okay. That I think makes sense. There's a subtle difference, right? I think.
And then I think I have the same question, which is if the next state is a function of a probability, right? But does it mean that if the probability is of a slip, then that slip behaves as if a different action had been taken, or we can land anywhere in the board?
You can't really land anywhere in the board. We don't want to model that. More realistically, you can land anywhere in the 4 adjacent cells. Like what we were discussing just now, if you are in state 0 and you take action east, then with 90% probability you go to state 1, but with 10% probability you end up going up or left or down, and depending on which one gets executed, you will end in a different state.
Okay, but with the 0 probability, you're going to land outside of the immediate adjacent cells.
Right.
Okay.
That probability is 0.
So one more question. This function does not take the prob slip as a parameter, right?
Yeah, this should be the other function, right? Set state transitions. The content here should be for the set state transitions.
Yes, that's my bad. Yes. Right. There were 2 functions to complete. This shouldn't be get next state. Yep.
Why are you doing a plus equals for the probabilities instead of just an equals?
because it will, if you think of any cell, then you can reach it from multiple locations, right? Because perhaps if you think of a cell, then you can come to that cell from any of the 4 adjacent cells. So you have to accumulate the probabilities.
It's because of the random action versus random state. If you do random state, you can use equal. If you do random action, you have to do plus equal.
Right, right.
No, even with random action, you still don't need plus equal, right?
You do because
Because-
there's multiple actions can hit the same location.
Well, the P is a tuple, right? So it has the original state, action, and the next state.
It's just that multiple actions can hit the same.
Right.
Because remember,
So
it's
if you think, yeah, so if you think about the next state, then that next state can be reached from multiple other state and actions, right?
Yes, but P is it also has original state as its index, right? So you won't be able to.
but just remember,
hit
it's because there's bad actions. It's that multiple bad actions, and the bad actions are all the bad actions aren't in the P object, right? So this in this notation that he's got here, bad action index, those are all those are being lost, and multiple bad actions will hit the same table location. Again, top left corner, you're trying to go north. Bad action east also goes north.
Yes, but that would be top left P state is top left, action is east, and it's hitting the original
the action
state.
is north, right? Because if the bad action is east, if it's the action's north, bad action is east, that's still going into north, and it's still hitting state 0. It would be like 0, 0, 0, right? Or I don't remember what north is, but anyway.
Well, yeah, 0, 0, 0, but the other one is 0, 1, 0, right?
It's not because you don't use bad action index, you use action index.
Yeah.
Because these are the probabilities that you took north, but you got east, right? So it's still a probability with respect to like north.
So can you show us your implementation with the bad states versus bad actions that we have implemented over here?
Did you want me to just copy paste into the chat?
Yeah, or I can just stop sharing my screen and you can show us, like you can share your screen, if that's all right.
Sure. Give me a second. I actually wrote both in the so this is it has both in it. Can you guys see?
Yes, yes.
So basically I have this little thing saying if random select action. So when this is false, it's when we get into so this is what I wrote initially, which is very similar to what you have. And this is the random select state. So actually the random select state's pretty easy. So in again, the same kind of structure, if, going through all the current states, going through all the desired actions. So in my notation, I've called it selected action, and the desired state is the state I was trying to get to. And then what I basically do is I create a set of all the possible states. So this is just a set where we go through and get, likely next action on action for all the possible actions that could have occurred. So, we just go through all the actions and get all the transitions. And I put this into a set just to, remove any duplicates, convert it back to a list. So what this ends up being is all the potential destinations that we could have possibly got. So then the probability that we have to put into all of those states is based on the, how many possible states there were -1, right? So there's n possible states. One of them was the desired state, so we take that out and you divide your probability slip by that.
Yeah, right. Yeah, right. No, this makes sense. But wouldn't this create a very different looking probability distribution? If I understand this correctly, then it is entirely possible. Like your distribution will be over all the 20 states, right?
No, because the possible states, this possible states is only populated by trying each action. So this set is only the states that I can get to from going either north, east, south, or west. So in the middle of the table, this is going to have 4 entries, but at the corners, it's going to have 3 entries, and on the sides, it'll have so the corner. Yeah, you should.
Corner has 2 and side has 3, right?
Corners has 3, I think. Sides have 4, but one of them is the current, right? And everywhere else has 4.
Oh, okay.
Yes. Yes.
And then, yeah, so this is just 3 or 4 locations. So you're dividing by either 3 or 4. And then, you just go through each of the possible states. And if the current, if the possible state was the one I want to be in, I add 1 minus this, and I just equate, equals, and then otherwise I get the other probability. And then we do get the desired,
Yes, you should sum up to 1.
Yeah.
Okay, this makes sense. Can you also try printing some of the individual probabilities, like what is the probability distribution for, let's say, 0,0?
I can show you. I have some print statements that I think will show what you're asking for. So what I did, I just printed out for each one. So like for 0, 0, if I want to go north, I end up with 0.9%, like 0.9 of actually getting that, 0.05 of going west, 0.05 of going south.
Okay.
So if I want to go east from that location, right, I have 0.05 of staying put, which is both north or east actions would be stay put.
Right.
Or sorry, north or west. Sorry, I mixed up mine. Yeah. Anyway, yeah. So west, so if you're going east, 2 actions hit this and were 0.5. 1 action was the desired, and then there's also, I could have slipped south as well.
Yeah, this definitely looks different than what we will get with the
well, in the steady state though, you're going to get the exact same, right? Like in the middle, it's handling the corners in such a way that it ensures that
right.
Yeah, it's random state, not random action. That's all it is.
Random action,
Yeah, I think the ambiguity comes from the problem statement. If you can go up to the problem statement, it says, yeah, thanks. So it says, the game ends in one of the incorrect states with a small probability slip. It might be better to say the game ends in one of the no.
Sorry.
Step 1, make the environment stochastic.
Yeah.
And the
second. That's why I read this. Yeah.
Yeah. So I think the second one might be better if it says the game ends in one of the incorrect actions with a small probability. Then that's.
Yeah, that's right. So I think instead of changing this description, I need to change the code, because the idea is same, that the action is not where probability is involved. The action is deterministic. The outcome is probabilistic.
I can copy this into the thing. But yeah.
Yeah, but I think in your implementation, still no need for plus equals, right? It's
I didn't need in the.
I mean, not yours. I mean the code.
In my implementation, there will be a need, because different, we can actually.
But from one state, there's only one bad action will lead due to a specific next state, right? I mean, there's only one way you go from one state to the next state.
Yeah, actually, I agree with you.
So I did it that way. So the whole reason I found out that this was needed was because I did it without the plus equals at first, and then I ran his next set of code and it didn't work. Or like I was printing stuff and you could see that the 0.9 was getting overridden. There are certain places that you can't, like if you print inside there, you'll see that it just doesn't work. Yeah. And that's actually why I was like, oh, hey, there's some ambiguity here.
Yes, that is right. I had forgotten the plus equal, and when I implemented it, then I was getting a lot of zeros. And that is how I figured that out. But yes, this implementation is, yeah.
So I think it's because you have a double loop. You don't really need the for action in bad action loop. You just need to determine that the next state is resulted from a bad action, not the action, right?
So yeah, that's exactly the second.
So you're saying, yes, we don't need a bad action loop. That's right.
Yeah. So your bad action loop so so both of your intended action loop and bad action loop is overriding the same cell, right?
I guess for some corner cases on the edge, maybe the right action, bad action will land on the same state, right?
Yes.
In some, yeah, I guess.
Yep. So there's definitely some issues with this implementation. So I will instead use the bad states code. Right. Did you share it on Slack?
I just dumped it into the chat for this meeting.
Oh, cool. Yep. It actually gets messed up in the chat because I think it eats all the formatting. Can you please share it in Slack?
I'm still logged in.
Okay, trying to.
Yeah, sorry, it's just I think you can still, I don't think you need this though. I think it's very small delta, but yeah, I'm just logging into the Slack. I'll send it. Like, I think it's just going to affect the corner slightly.
Yeah, I guess the corner is the main problem where if you go to the south or east, it might you stay in the same spot.
Right. Cool, no issues. So please share it in Slack whenever you log in. I think we can even move ahead with this implementation. It's not exactly what we wanted, but yep. So let's just try to execute this for the time being. Right. And if we look at the probabilities, right? So for a corner case like this one, uh, you are getting 0.93 for the 0th state. So this means we are taking action 0, which is north. And what you get is, of course, because the correct action will bring you back to the same state. So 0.9 probability goes here. And then the rest of the 0.1 probability gets distributed between, in this implementation, between east, west, south, and east, west, and south. And because going west will again bring you back to the same state, so that 1/3 of that probability is getting added here. So that is why you have a 0.93 over here and a 0.3 corresponding to going east and a 0.3 corresponding to going south. And if we look at, for example, state 1 and action 0, right? And in this case, going north means again remaining in the same state, so 0.9 over here, and then the rest of the probability is distributed between going left, which means going to state 0, or going right, going to state 2, or going down, which is state 5, right? And so this is how it will, this is under the assumption that this is happening of actions being random, not outcomes being random, which needs to be corrected, right? But for the time being, if we just assume that this is the probability distribution that we have implemented, and then we can just interact with the environment a little bit, see if things are actually probabilistic. So right, I'll try going east. There seems to be a problem. Oh yes, yes. So we have implemented this piece of code, but we still have to implement the other function, which was the new definition of get next state on action. So this is not going to look a lot different from what we had earlier. Again, right. So there is a little bit of conversion that is needed because we get an action over here, and because our table is basically a NumPy array, so we are using indices, not string labels. So convert the action to an action index, and then we are just sampling from the p table. So this is a list of states, and this is the probability corresponding to those states. We have specified the starting state and the action state, action index. So this will give us an array of size 20, and then you sample from those states. Of course, the way we have implemented it, only 4 of the nearest states will be having non-zero probabilities. So what you get here is one of those 4 states. So with these changes, with these changes, we should be able to now run the environment and explore it. I don't know why it's taking a little bit time on my side, but try to explore the environment, run this piece of code in step 2. Okay, it's taking time because we haven't terminated. Yeah. Right. So in this case, I tried going east, but it actually ended up staying in place because of the randomness. Let's try again. This time it actually did move. Right, we went south, east again. So most of the time it is behaving correctly, but occasionally you are seeing that random pattern emerge, right? Which is expected. Right. This piece of code is what we had used earlier. So again, we are going to reset the reward structure. And then the question is if we need to make any additional changes, right? So get discounted return will remain the same. It doesn't really get affected by whether or not it's probabilistic, because if you think of how it is working, you are feeding it actions and then you're getting new states back. So even if it is probabilistic, you will only get one next state and one next state out. So whatever that is will depend on exactly what the value of p slip that we set over here, right? This value. But in the end, it is going to be one state. It's not going to be a distribution. So there are no changes required. Think about it. But if we leave it as it is, and the next two cells are again they're not affected by any of these changes, right? Uh, what about step 3, where we are generating random actions? Is there a need to make any changes because now the environment is not deterministic anymore? So I think if you look closely, we don't require any change here again, because again we are simulating an action, and of course that action is now not deterministic anymore, but whatever state and reward and that action produces, that is okay, because we are just randomly feeding it actions. There is no change that should be needed here, right? And the same goes for the next cell where we are computing discounted returns. Again, discounted returns it's like you have an entire episode that has already been generated, so it has nothing to do with the probabilistic nature of the environment, right? What about greedy episode generation? Do we need any changes over here? Do we think any changes would be needed here in this code, because now when you take one action, multiple states are possible?
So in this case, the self dot actions, we need to like multiply by self dot probability.
uh, Self dot actions.
No, not self dot actions, just the actions being like multiplied by self dot probability. I mean, like foosball dot probability, we need to multiply.
But why would we want to do that? Because actions is something that is coming from outside the environment,
Okay.
right? You feed it any action, like I would instruct the environment to go east. Now, because the environment is itself probabilistic, it may not actually end up executing that action. But isn't that what we sort of want to learn, or sort of want to collect in terms of data? That okay, we took an action east, and many times you would notice that action east in a certain state actually took you east, but sometimes you would notice that action east actually took you down or somewhere else,
Sure.
right? So I think there are no changes required here either, right? And then we come to the first algorithm that we implemented, which was able to converge, and right, and think about whether we require any changes over here, right? So we have already gone over all of this. We are generating episode, then we are finding the discounted return, and then we are using that to update. So do you think anywhere in the update step or anywhere else any changes are required? Yep. Actually, no changes are required here either, because again, this is all based on sampling, and the sample will no doubt produce some bad examples as well, where you took the right decision, the right action, but the outcome was not the desired outcome. That will sort of uh, throw you off track, throw your learning off track a little bit. But as long as the p slip probability is low enough, it shouldn't be an issue. Perhaps you would need more episodes, because now sometimes you see this stochastic action probability in play, and whatever the expectation was, the outcome is different, and that sort of delays the learning process. It confuses the algorithm. But because it is again based on sampling individual steps or individual episodes, So it shouldn't really matter whether internally it is a deterministic environment or it is an environment that has some probability involved in it, right? And if you run this code, right? So we let it run for 5,000 steps, which is the same you know number which we were using earlier. And if you look at the policy, it still seems to be doing a good job. So with 5,000 steps, the policy is almost optimal. There are these two states which I think we weren't getting right earlier as well with 5,000 steps. But generally, this is the same policy that we were getting in the case of a deterministic environment, right? Uh, and then if you come to the TD learning part where we implemented SATSA and Q learning, so there is again no need to change the logic of the code, right? The logic remains same. It is again based on sampling. What we may want to do, or what we may have to do, is that run the code for 2,000 steps. We were able to get a decent policy with 2,000 steps earlier, but now we will have to check if that is still the case. Right. So even now with all the same parameters, with a epsilon decay of 0.995 and an alpha of 0.01, we seem to be converging to the right policy. Right? Is everyone able to run this code and get the correct policy most of the time? Are these the same parameters that we were using last time? So just try to experiment a little bit. I think the alpha value was much smaller last time, 0.001 or 0001. That was sort of giving us good results, if I remember correctly. But if you use the same parameter this time, yeah. So with an alpha value of 0001, we don't quite converge to a good policy. And throughout the training process, there doesn't seem to be a point where we are anywhere close to a good policy. So this is something that needs to be tweaked. Let's try making it. Yeah. Even with 10 to the power minus 2, it's not converging fast enough. right. But as you increase the alpha value to 0.01, we seem to be getting the right results. Again, these two states are still not optimal. The policy is not optimal, but the rest of the policy is pretty much like what we used to get earlier, right? Um, and then let's try the Q learning part again. Again, alpha is set to 10 to power minus 4, which is what we were using earlier. Oh,
So in principle, is it correct to say that you just have to sort of account for the probabilities in the initial environment setup, but after that, nothing else changes except that you might need to take longer to converge so you can average out noise?
yes, that's right. So as long as you are using one of these approaches, if you're not using the dynamic programming based approach, which we had abandoned much earlier because it wasn't going to help us in dynamic situations like this one. So as long as you are going to use this sampling based approach, be it sampling an entire episode or sampling one step at a time, then you really don't need to make any changes to the algorithm. But yes, it's very likely that you will have to run the algorithm for much longer, because obviously the algorithm is now trying to learn the probability distribution as well. So it's trying to find out which is the best action to take, while some actions are non-deterministic, right? And along with that parameter, which is the number of episodes, which you might have to increase, there might be other hyperparameters like the learning rate. So 0.01 doesn't seem to converge fast enough. So there are two options. One is you can take up the number of episodes to 20,000 and then see if that is working or not. The other option is to try tweaking alpha, that like what we did with with SATSA. So try increasing the value of alpha, make it try to learn faster. Uh, how do I know faster will work? I figured that out from trial and error. I didn't have a good theoretical basis for that, but making alpha close to 0.01 in this case, that seems to work.
Would it make sense to spend longer on exploration? I mean, intuitively, I would think that early on you might just get unlucky and end up, at the wrong sort of,
Right.
nominally optimal state. But if you spend longer on exploration, you would hopefully, average out noise from that and end up at a better place to
Absolutely.
exploit.
So that is what I was also thinking, that since this is inherently probabilistic, so you want to spend more time and you want to set this value of epsilon decay to a higher value, right? And there are a few sort of experiments that you can do, which we will talk about in a moment. But before that, what we want to do is we want to understand, we want to be able to measure how, if and how the algorithm is converging or not. And what we want to do is very simple. We will store the reward for every episode, and then at the end of the training, or even during the training, we will print the running average of that reward. So for every 100 episodes, I will find out what the running reward is. Now in this case, I don't know what the sort of don't know that what the optimal reward should be. So we're not chasing an exact number, but we will still take a look at the training process, and we'll see if the reward saturates at some point, right? So if is 2000 steps adequate or not, and then if I'm going to change alpha or if I'm going to change epsilon, uh, how many episodes should I train for, right? So very simple ask. We need an numpy array or a list which should just get filled with the reward at every episode. And then after this training process is over, we need a little bit of code over here that will take that array and it will compute the running average over a window of size 100 episodes, and then we'll plot that running average. Right. So what we need to do is, outside the loop, you need to define an array. with the same length as the number of episodes, and then just fill that array at the end of every episode. That is sort of the first step. Right, so we just define an array, or it could be a list, and then at the end of every episode, outside the while loop, we will so we need a variable to track the reward within an episode. We initialize it to 0 at the start of the episode. Then within the episode, we are just going to keep accumulating. Right, and at the end of the episode, I store it in my array. This is trivial, so just run this part. Okay, right, so this time we didn't get exactly very good policy, but that aside, what we want to do is now we want to take that entire array of size 2000, yeah, 2000, and we want to find the running average. So it will be like the first entry uh, in the result should be the average of the first 100 episodes. Then the second will start at the second episode till the 101st episode, and so on. So there is an numpy function called np.convolve, right? Uh, this actually performs convolution. Convolution is like you have a signal or some sort of a data, and then you take a window, which is again sort of weights, and then you slide the window over your data, and at every point, at every index of the data, you take the weighted average. So you multiply the weights in your window with the data in your array, and then you sum it up. That is the idea behind convolution. So just look up the numpy convolve API and try to implement this 100 episode averaging. Okay, so if you look at the API, just take three parameters. One is your array or signal or whatever you call it. The other one is your window. Uh, right here, we want a window of size 100. So I'm just passing it, in a by array, which is just of size 100 and filled with ones. We can actually divide this by 100 over here because we want to take the average, so we want to multiply every number, every of those 100 rewards by sort of 0.01. So I divide it by 100. And then the third parameter, valid, basically when you're sliding this window and across the signals, then the third parameter decides how far that sliding will go on. And in case of valid, it will stop the moment your window is trying to go beyond the right end of your data. So with these settings, and then yep, this looks a lot zigzag, but the good thing is that if you look at the 1,000 episodes, so it is still climbing up. And you will always see, even with deep learning or other approaches, these variations will be there, right? Even with a window of size 100, there is a lot of variation. The algorithm sometimes learns, sometimes unlearns things and start to perform poorly. But as long as the overall trend seems to be climbing, we should be good with more episodes. So if you increase it to 3,000, 5,000 episodes, then it's likely that this graph will gradually go still up, and we will get we will be able to get better rewards, right? uh, if instead of this it has saturated and the trend will be like a flat line, then obviously you need to tweak other parameters, because increasing the number of episodes would not have helped. So this is the first thing you could do to debug your algorithm. Do you need to do you need to wait for more episodes, or do you need to tweak something else? And this is sort of the first thing that needs to be tweaked, right? The next step is basically implementing another variant of SATSA. So the one that we are using over here, this one, it takes out one action in the new state, which is greedily selected, and then we select the reward corresponding to that action over here, right? There is another variant which does not use A1. It actually takes the weighted average of all the possibilities. So obviously in state S1 there are 4 possibilities, because there are just 4 actions, and the policy that we are using, it's an epsilon greedy policy with a particular value of epsilon at that point, right? So you want to look at all 4 possibilities instead of just taking one of them, sampling one of them, right? And which means that there is, first of all, there will be a change in right here, because now, sorry, there will be a change in the update step, because now instead of taking S1 comma A1, we need to take the weighted average of all the return values corresponding to this state. So sort of, we don't need the action over here, we just need the state, but this gives you an array. Now you need to weigh that array by the corresponding probabilities that come from your epsilon greedy policy, right? So let us try to implement that. As the last step for today, we will try to implement the expected SARS algorithm, which is going to look a lot like our current implementation, but there will be at least one change over here. Okay, so let's go back to breakout rooms for another, say, 15 minutes and try to implement this. And feel free to like look up things, search the internet, find out what exactly expected SASA does compared to our current implementation, and then implement that.
Hey, Farhan,
Yep.
can I ask you a question? So how long are you going to keep the videos on YouTube up?
I think they're going to remain there.
Okay.
Because I think as per my contract, we may have to share them with additional learners who want to learn on their own time.
Oh, okay.
So I think they will. I don't really see a reason to remove them.
Oh, okay. All right. So they will be still in that playlist.
Right.
Yeah. Okay. All right. Thanks. I have been jumping in and out of the calls today because I have a customer thing. But I tried the project. Yeah, I mean, let me know if it is the good time to talk now, or maybe we can talk later. Yeah. So I was always getting from our SARSA and Q learning values which were like negative 500. They started with negative 800 and came up to negative 500 or so.
Right.
And I tried something which is basically trying to use greedy pickup or action for the first 500 or 800. That kind of pushed it up to like 300, negative 300, not really. But right now, after some Google search, I found something where one of these guys was trying a uniform distribution to pick to whether to do a greedy selection or to do as a selection using the step function from taxi v3, and that sort of pushes up to 7 directly.
Okay. What were your parameters? Like, what was the episode length when you were using the simple approach?
Well, the max episode length was actually 25.
25 could be a little on the lower side because the taxi first has to travel to the pickup location, then it has to perform the pickup, then it has to go to the drop down location. So could maybe making it a little like 50 should be adequate, because you can think about the longest travel distance that might be needed.
Oh, okay. Because I thought 25 in terms of there are actually 5 by 5 locations. So
Right.
maybe I thought that was 25 would be.
that was adequate if we just had to perform say pickup, but now you also have to travel back and
Oh,
drop.
okay. Oh, okay. All right. So, well, my point was, one other thing was that with that guy's code, which I'm going to submit with the link as well that I refer to it, so you know that I've used that. It still goes to 7, and I tried with a bunch of parameters, changing the gamma and the alpha value and all, but tops I can get is a few values in 8, but nothing close to even 9. Forget about more than 9.
Okay.
So
I think epsilon plays one of the most crucial roles.
Okay.
How far you are keeping it random, and where do you so two things. One is the minimum value of the epsilon that you set, which is I think 0.1 in our code. And then how quickly you are tapering that off, how quickly you are decaying the value of epsilon. In my when I was toying with the code, then that seemed to play a big role, just decreasing epsilon and increasing alpha, which is the learning rate.
Okay, decreasing epsilon and increasing alpha. So is it like should I decrease much faster, or maybe?
Yes. So you want to end the randomness much quicker. So perhaps something like 0.999. If that is too high, then try 0.99. Perhaps that will give you faster convergence. And the learning rate also, I believe, is something like 0.01 will be much better.
Okay. So I guess we never increased the learning rate, right? The learning rate was always constant.
Yeah, it was constant. We can we might want to decrease it. That is something we can do in the beginning. Keep it at a higher value, then gradually taper it down, just we are doing with epsilon. So a similar approach with learning rate. If you are using like 50 is not a big number, but if say I was using 200 as the episode length in the beginning because I just wanted it to explore and find out the solution on its own. Then I can also control the episode length. Then that also naturally shortens as well. As if you look at the time it takes, for example, I was using TQDM outside the for loops, and I was just noticing how many iterations the algorithm performs. So in the beginning, it starts with like 50 iterations because it's taking it on a lot of random actions, and that is taking time. But the sooner it hits like 1,000 iterations or so, it has learned to a point where it is most of the time it is able to figure out the correct solution. So then the iteration time or the number of iterations really goes up from 50 to say 500, tenfold or so. That is also an indicator.
I saw that. Yeah. One last point that I realized was it was right in front of me. All right, I'll get back to you. I
Sure.
totally skipped
Just
my mind.
ping me on Slack.
Sure. Thanks.
Sure.
I realized the terminal state. Do you think so? I walked around the terminal state a little bit, and first I tried it with the terminal state, which was I set the drop-off location as the terminal state. But then a few web searches realized that nobody was really using it. So does this problem actually have a terminal state?
Yes, it does. You can consider it an episodic task, and you can actually use the done flag, right? So,
yes, yeah, the done flag. So that's what they were using, the done, and not really the terminal state sort of thing.
Right. So instead of directly trying to detect the terminal state, let's rely on the done flag. If it is an episodic problem, then the done flag, of course, will be set when you drop off. And I think that is what is happening, right?
Yes, that's what is happening actually. The done gets set.
But we still want to cap the number of steps in an episode because in the beginning, it might just go into an endless loop.
Okay. So here, this is not episodic. Like once if you drop it off, isn't that ends the episode?
Yeah, it does end the episode there.
Okay. All right.
But in the beginning, because if the policy is bad, you could just be stuck somewhere, like trying to go north when there is no way north. So to get around that, you want to cap the number of steps.
Oh, okay. All right.
Sure.
Excellent. Thank you.
So absolutely. I think everyone gave it a try. This is a lot more similar to Q-learning than the SARS algorithm. So here is my implementation. And if you look at it closely, it does look a lot like the Q-learning algorithm, right? So we select an action A0 in the current state, and that gives us the new state. But then we don't really sample once again, which we were doing with the SARS algorithm, right? What we do instead is we would require some sort of return value here. So we take all the return values for S1, and then we weigh them by the probabilities of our greedy policy, right? So it's like saying, if you consider, because this is the policy we are following, if we would have taken the next step, then there are 4 different outcomes and they have different probabilities. So let's just weigh the return for all those different outcomes. This is what is going on over here. In case of Q-learning, we just take the max here. In this case, we are taking the dot product of these probabilities and these return values. And of course, because there's no action A1 over here, so that doesn't get updated here. The rest of the code is pretty much like Q-learning or SARSA. When I run this for 2000 episodes, it seems to converge almost correctly except for this state over here. So this has some properties. I shared a link which I'm going to share again. Right, so this is another possible variation other than plain SARSA and Q learning. Right. So that sort of finishes all the work that we needed to do today. Again, the code over here needs to be corrected. There are two issues with this code. One is these two loops aren't really required because we are going over the same actions twice. So that has to be removed. But this still is implementing randomness in terms of actions, not randomness in terms of outcomes. So that needs to be replaced. So think about it for once and then try to implement randomness in terms of outcomes, right? So given that we took an action, what is the probability that we ended up in some other state? And what we want to do next, which is a tomorrow session, is we have added a little bit of realism to this setup, but now we want to make it a lot more challenging for the agent, right? So even when we introduce the probability here, the agent seems to be learning quite quickly. So why not add more realism? And the way we want to do that is we will make the other agents uh, a little more intelligent. So in the beginning, we don't want to introduce too many changes all of a sudden. So in the beginning, we will just allow the agents to move, right? And we will allow the opponents to move, right? This is what the notebook I'm showing you is for tomorrow's class, but this is what we are going to the changes we are going to make, right? So instead of being static, now they can move. We will still restrict them to their columns, so they cannot go move horizontally. They can move vertically, and the movement is still going to be just random. So all the agents will just wiggle up and down, and at any instance, it is more challenging than a simple situation where agents were fixed and you just had to find the shortest path, right? Now, when you think about that problem and solving that problem, one thing we should realize is that now the agent cannot be blind anymore, because so far all the agent cared was about its own position, and we were expecting it to find to learn how to find the shortest path from the beginning to the end, because it will go through the same field again and again, so it will sort of figure out where those static obstacles are, and then it will know which action to take to avoid them, and that is what it is sort of has been doing. But now when things get dynamic, so we also, if we just stick to the earlier implementation where the state that is visible to the algorithm is just the position of the ball, then that is going to be really difficult in terms of implementation, right? Expecting the agent to learn when it doesn't really have visibility into what is going on in the environment, uh, that is not a good idea. It won't converge. What we want to do instead is we want to broaden the field of view of the agent. So instead of just knowing about its own position, now the agent will be able to look around to some distance, right? So what we want to implement is that, okay, the agent knows about its own position, and the agent is also able to sense if any of the four adjacent cells has a defender present there or an opponent present there. So now the state is going to change, right? So there are two main changes. One is that we are allowing for the movement of the opponents, and then we are going to change what state the agent is able to view or the algorithm is able to view. This is what we will do in tomorrow's class, and we'll see how this makes it more complex for the agent to learn, and if we need to make any changes to our algorithms to first of all first of all we will need to make a lot of changes to our implementation of the class itself, the football class, because now you have to encode the states. So there are really uh, several pieces of information about the position of the player, uh, sorry, not the position, but whether the players are present or not, and then where the ball or the agent is. So you need to encode that into a single variable that we can again call our state. So we'll think about that encoding and decoding, and then how that affects the rest of the functions. We will implement that first, and then we will see if the current algorithms work or if we have to tweak those algorithms to, deal with this kind of situation. Cool. So that is everything we had for today. Uh, Tomorrow, I already gave you a glimpse of what we are going to cover tomorrow. That will also finish, the module 1 of this course, which was the introduction. Uh, and on Monday, again, we will have a few slides, the recap, and obviously a little bit of extra terminology. Because when we made these changes, when we moved away from from a deterministic world to a stochastic world, then we didn't really make any changes to our algorithms because they are all sampling based. But in terms of equations and formulas, there is a change. So we should know the theory around that. So I will include that. There was one slide about Bellman equations, which we haven't really talked about uh, so far. So I would want to include that on Monday's slide. But yeah, by Monday we will have everything that was there on the syllabus for this that will be covered. The only remaining thing will be the project, and I was discussing that with Akshay a while back. So if there are, if you're facing any issues, then feel free to research the internet, but then also cite your source and also make sure that you do some exploration on your own before just falling back on one of the existing implementations and just using their code. First experiment, try to get the best result you can, and then of course whatever uh, bits of research helps you, any anything, any sort of improvement that you are doing, you're able to include from external sources. You feel free to do that, and but do cite them in your notebook. And if there are questions, you can post them on Slack. You can also use the same Slack channel to discuss it with your fellow learners.
So regarding the project, I had a quick question or two. Are we able to, if we want to extend the taxi API, or do we need to use the API as is? Like, can we just make our own class that inherits from taxi and add some more useful functions like get state and stuff like that? Or do we have to use the API as is?
I think there's no issue with extending the API as long as we are not touching the reward and the state transition matrices.
Yeah, so that was actually going to be my next question. So they have this like P object that has, all of the useful information, but it's not really exposed through the API. Can we play around with that P object and have things like get reward for transition and use terminal state and so on? Or, at least to
We don't
implement
want to
dynamic
do
programming?
that because we don't want to do that because then that just that is like that becomes a toy problem, right? Because that is what the approach we use with foosball in the beginning, where you are able to peek inside how the transitions happen, and then you can just use dynamic programming to learn them.
Yeah. So I guess what I'm asking is I understand that at the end of the day, we want to not have that visibility, right? But would it make sense to sort of write APIs that give us the visibility so we can, try dynamic programming and verify that things like our get reward is working?
That is perfectly okay. Yeah, if you want
Okay.
to benchmark it, then please. Yeah.
Okay, yeah, so like just to pipe clean, for example, our, that we are getting rewards correctly from the episode and stuff like that, right? And then as long as our final solution isn't using those APIs, it's acceptable if we have them.
Right. So the solution should just use existing APIs, but if you want to do some sort of debugging or benchmarking, then it's okay to add a few functions and then even look inside the P matrix.
Cool, thanks.
Sure. Cool. Then let's wrap up for the day. Yeah.
Farhan, I also had a question about the taxi problem. In terms of the training, what is a good number of episodes that we can run up to? Like, should we expect certain numbers that as to how much episode we should be training for, or are there any like limit or in terms of maximum as well? Because if there's at a certain point, if you try like a really large number for the episodes, but it's still not converging, I'm sure it's something to do with the hyperparameter rather than the episodes. So just wondering to see what is a good number for like training the episodes.
Yeah. So the first thing we need to figure out is what we were doing today, which is doing a plot, the running average. That sort of tells you if increasing the number of episodes helps or not. Now, how many episodes you are going to need, that of course depends on the other hyperparameters, your learning rate, your epsilon, uh, the episode length, all of them are going to affect things. But my guess is if you plot that the running average, then you will see that most of the learning happens in the beginning, and then that plot saturates very quickly. So you would need somewhere between say 10,000 and 50,000 steps to converge. And if you are requiring more than that, then perhaps you can very easily just increase the learning rate perhaps, and you can shorten your learning cycle. So too many episodes, like 200,000 episodes, that shouldn't be required.
20,000 episodes should be required.
No, 200,000 shouldn't be required. 20,000 is fine. 10,000, 20,000, 50,000 should be fine.
I see. Okay. And we don't really have to touch the gamma parameter, right? Like that's usually set to
can.
0.9.
We can even set to gamma to 1.
I was also wondering if you had some suggestions on making something analogous to pretty print.
Yes, that is the difficult part. I was thinking about it. The way states are encoded and the number of states, that make it very difficult to eyeball the whole thing at once, or the policy at once. What you could do is cherry pick the bad examples, just keep track of instances where you're not getting good rewards, it's very negative, and then log them somewhere along with your Q table and whatever other information you need to reproduce the path that the agent took, right? And then you can just because there's a decode method inside that class, so that should let you convert from the state action pair uh, to like a policy that shows you the route that the car followed.
Yeah, because I guess what I was struggling with is, so the states here, it's not just the location on the board, right? The states here also encapsulate information about whether you've picked up the passenger yet, and stuff like that. So if we just had something which shows the location on the board with an action being like an arrow of the direction that you go, that's not quite sufficient, because you also need information about, have you already picked up the passenger, or are you trying to pick up the passenger?
Yeah.
So
right.
that's why I
it
was.
won't be a snapshot. It is going to be a sequence of things that you will have to look at.
Okay, so there isn't really something that's analogous to pretty print for this problem.
Yeah, that doesn't seem possible.
So I was thinking on the same lines, but I was wondering that, so, we have this X and Y coordinates, and then we have, let's say, the position of the pickup location.
Yeah.
And what if for that X and Y coordinate, if there is a pickup location there in, all the 5 different variations, 5 or 6 of them, I think 5 different variations, why can't we just skip everything else other than the one that actually has the pickup location and just display that? Are you getting my, like, I know you have it's a tensor of 5 by 5 by 4, right?
Right.
But maybe the 5 and 4 can be selectively, you can select only the ones that you need.
Right. So fix the pickup and the drop off location.
Yeah.
And then on top of that, print the directions that the taxi took, right?
Yes. But the thing is, I'm still stuck at, or wasn't able to figure out which ones to really pick, because I did not actually haven't still able to think through that, but I was just trying to throw an idea here, which
but the decode function should help you, right? That once you decode your current state, that will give you the exact row and column for everything.
Yeah, I guess the tricky part is that you don't know if you're in a specific location, are you trying to pick up the passenger, or are you trying to drop off the passenger, right? So you would need at least 2 plots,
yes.
one for the arrows that you get in a state when you're on your way to the passenger, and one for the arrows that you get when you're on your way from picking up the passenger to the drop off.
But don't they already have a color scheming, right? So when you are about to pick up, then the cab is yellow, and when you do a pickup, then the cab is green. So if you use the render API or something similar, then you can implement the same logic.
So for plotting the state, yes. The question is for plotting the policy. You would need a way to distinguish, because what we have when we plot the policy, right, is we just have an arrow telling you the direction to go when you're at a particular location on the board. What we really want here is not just one arrow. We want an arrow along with information about whether that arrow is going to the pickup or whether the arrow is going from the pickup to the drop off.
Yeah,
I guess we can have 2 different policies. One is to the pickup and one from pickup to drop off.
Right.
Right.
Yeah, that is the way to go. So plot them separately, the pickup and the drop off.
Okay.
And what like I was discussing a while back, which is just being able to plot your the running average of the reward. That should tell you about how well you are performing when you are tweaking different parameters. Keep everything as changed, change one parameter and see what effect it has on the number of the number of iterations it takes. And you can also keep track of the episode length, and you'll see that the episode length quickly drops off. So whatever you have set it to 50, 100, 200, that should become a lot shorter very quickly. And I tried over the last day or so, I just tried playing around with the environment taxi v3, and I just tweaked the parameters a little bit from what we had set in our classroom code. And I think I was easily able to hit something like 8, perhaps something between 7 and 8. It wasn't getting it consistently, but I was able to touch 7s and 8s, and then in between there were points where the reward would go down. But that was just with a little bit of tweaking.
So for this test or the rubric, we need to always consistently hit over 9, right?
Yes.
Okay.
Also, Farhan, regarding the negative reward in this taxi problem, or maybe the penalty, there is no penalty as such when we drop off the passenger in the wrong location, wrong destination, right? Like one of the other three, or is it encapsulated in the -1 step?
There is a -10 penalty for a wrong pickup or drop off, right?
Wrong location in the sense, not in any of the other three. So if we drop off in not in any of the other three locations, then the reward is -10. But if we drop off in one of the taxi locations, that is 0004, but which is not the destination, then there is no penalty. If I understand it correctly, or maybe
I think there's a penalty, but
okay.
Double
Okay,
that.
I'll double check that. Thanks.
Is there any discounted returns here? Or should we just always be assuming the gamma is 1 for this problem?
No, you can discount them. We were discussing that a while back. You can use the discount factor, but because there is a penalty for every time step, then even if you set it to 1, it should work.
Well, I guess what I'm asking is, so when we calculate the number that we're supposed to compare to 9, right?
Yep.
When we do that calculation, we should be assuming gamma is 1, right?
At that point, you don't have to use discount. Discounting is only for training. When you are evaluating, you just want to find out the exact actual reward that you're getting, not the discount reward.
Yeah. So when we're computing the I guess the return for a particular policy, we should be using gamma as 1, right? Not using a discount.
Correct.
Oh, so do we have to have a separate evaluation step? Because I thought while training itself, you can keep track of.
Yeah, you can keep track of. We are not doing that post training. So this is the running average that you are getting during the training. Okay. You can also do something similar after the training is over. Then you can run like for 10,000 steps and then do 100 episode running mean.
Oh, okay.
But it sounds like if you're doing that, you would need to have a different calculation, right? You would have to have a calculation that uses discounted returns for the purpose of training, and then a calculation that's using gamma equals 1 for the purpose of evaluation.
Right. So you mean when you are doing evaluation within the training loop?
Yes.
Yeah. So within the training loop, you just need to accumulate the reward, whatever you're getting out of the step function. Just keep adding that. So there's no gamma involved.
Right. But the return that we are actually using for training, right? If we're using discounted returns, there would be a non-unity gamma. So there would be 2 calculations happening in the training loop. One for the discounted return, and one for the return that's the actual return with gamma equals 1.
Correct.
Oh, okay.
Cool. If there are any other questions, please post them to Slack. We'll try to answer them today. If not today, tomorrow morning. And let's keep working on the project. If you get stuck somewhere, then again, reach out to others on Slack. I will also try to help. And there is a survey that I'm going to circulate. It won't take more than 30 seconds of your time, but I just wanted some feedback around how this course went so that we can then adopt the second course accordingly. So I'll just circulate that in a little while on Slack. Please fill it, and then I'll see you on tomorrow. See you tomorrow.
So the last day of project is actually 7th of May.
Yes. So
Is that correct?
29, 30th today, right? Yeah, 7th May.
7th of May. Okay. All right.
Is there an office hour on Monday?
There is. Yes.
Okay. All right, cool. Thanks. That's all I have.
All right.
Thank you.
Thank you.